do you produce elementary particles? Electrons and protons are no problem. These are the stable constituents of ordinary matter. To produce electrons, one simply heats up a piece of metal and they come boiling off. If one wants a beam of electrons, one then sets up a positively charged plate nearby to attract them over and cuts a small hole in it. The electrons that make it through the hole constitute the beam. Such an electron gun is the starting element in a television tube or an oscilloscope or an electron accelerator. Figure 1.1. The Stanford Linear Accelerator Center (SLAC). Electrons and positrons are accelerated down a straight tube 2 miles long, reaching energies as high as 45 gigaelectron volt. Photo courtesy of SLAC. To obtain protons, you ionize hydrogen. In other words, strip off the electron. In fact, if you are using the protons as a target, you don't even need to bother about the electrons. They are so light that an energetic particle coming in will knock them out of the way. Thus, a tank of hydrogen is essentially a tank of protons. For more exotic particles, there are three main sources: cosmic rays, nuclear reactors, and particle accelerators. Cosmic rays. The Earth is constantly bombarded with high energy particles, principally protons, coming from outer space. What the source of these particles might be remains something of a mystery. At any rate, when they hit atoms in the upper atmosphere, they produce showers of secondary particles, mostly muons, by the time they reach ground level, which rain down on us all the time. As a source of elementary particles, cosmic rays have two virtues. They are free and their energies can be enormous, far greater than we could possibly produce in the laboratory. But they have two major disadvantages. The rate at which they strike any detector of reasonable size is very low, and they are completely uncontrollable. So, cosmic ray experiments call for patience and luck. Nuclear reactors. When a radioactive nucleus disintegrates, it may emit a variety of particles: neutrons, neutrinos, and what used to be called alpha rays. Actually, alpha particles, which are bound states of 2 neutrons plus 2 protons. Beta rays, actually electrons or positrons, and gamma rays, actually photons. Particle accelerators. You start with electrons or protons, accelerate them to high energy and smash them into a target. By skillful arrangements of absorbers and magnets, you can separate out of the resulting debris the particle species you wish to study. Nowadays, it is possible in this way to generate intense secondary beams of positrons, muons, pions, kaons, and antiprotons, which in turn can be fired at another target. The stable particles, electrons, protons, positrons and antiprotons, can even bifurcate into giant storage rings in which, guided by powerful magnets, they circulate at high speed for hours at a time, to be extracted and used at the required moment. Figure 1.2. CERN, outside Geneva, Switzerland. SPS is the 450 gigaelectron volt super proton synchrotron, later modified to make a proton-antiproton collider. LEP is a 50 gigaelectron volt electron-positron storage ring now under construction. Photo courtesy of CERN. In general, the heavier the particle you want to produce, the higher must be the energy of the collision. That's why historically lightweight particles tend to be discovered first, and as time goes on and accelerators become more powerful, heavier and heavier particles are found. At present, the heaviest known particle is the Z boson, with nearly 100 times the mass of the proton. It turns out that the particle gains enormously in energy if you collide two high-speed particles head-on, as opposed to firing one particle at a stationary target. Of course, this calls for much better aim. Therefore, most contemporary experiments involve colliding beams from intersecting storage rings. If the particles miss on the first pass, they can try again the next time around. Indeed, with electrons and positrons or protons and antiprotons, the same ring can be used, with the plus charges circulating in one direction and the minus charges in the other. There is another reason why particle physicists are always pushing for higher energies. In general, the higher the energy of the collision, the closer the two particles come to one another. So, if you want to study the interaction at very short range, you need very energetic particles. In quantum mechanical terms, a particle of momentum p has an associated wavelength lambda given by the de Broglie formula lambda equal h by p, where h is Planck's constant. At large wavelengths, low momenta, you can only hope to resolve relatively large structures. In order to examine something extremely small, you need comparably short wavelengths and hence high momenta. If you like, consider this a manifestation of the uncertainty principle, delta x delta p greater equal h by 4 pi. To make delta x small, delta p must be large. However you look at it, the conclusion is the same. To probe small distances, you need high energies.